Everyone, so today is my pleasure to welcome Simone Brugiapaglia, who will be talking about the mathematical foundations of deep learning, from rating impossibility to practical existing theorems. Yeah, thank you.
Okay, first of all, I'd like to thank the organizers of this wonderful seminar series for the work they put together to have this event, to make this event possible. Particularly, I would like to say thank you to Paul Median for his kind invitation to speak during his visit here in Montreal. I would also like to acknowledge collaborators that made this research possible over the years. They range from Canada to the US, and they're mainly people who I work with for the project I'm going to present today. So they are Matthew Liu, a former undergraduate student at Concordia, now working at Ubisoft. Then there is Dick Dexter, an assistant professor at Florida State University. Ben Adcock and Paul Tapper are full professors at Simon Fraser University, and they are my former postdoc mentors when I was a postdoc there. Sebastian Moraga is a PhD student at SFU, and Clayton Webster is a distinguished researcher at University of Texas at Austin. I'd also like to say thank you to the various sources of funding who made this research possible over the years. These are NSERC, the Faculty of Arts and Science of Concordia, le Centre de Recherche Mathématique in Montreal, and the Pacific Institute for the Mathematical Sciences. So we all know that we live in a so-called AI golden age. So that's a small histogram taken from the 2022 AI Index report by Stanford that collects all this kind of statistics related to the AI, the evolution of the AI field in industry and academia. Particularly here, I'm focusing on academia. This histogram shows the number of AI-related publications in thousands from 2020 to 2021. And we can see that in the last roughly 5 years, we are witnessing a linear growth in the amount of publications in the field. Of course, AI is a very, very broad topic, and there's many sub areas within it. And so the main topic of interest for the seminar is of course machine learning. And if we dig deeper into statistics and we see how many publications per subfield in AI have been put out in the last from 2010 to 2021, then machine learning is the one that has the highest kind of increasing rate over the past 5-6 years. That's the light blue curve. So we have also witnessed, and I will be fast in this kind of seminar, I probably don't need to justify this very longly, but we have seen that the AI revolution has been driven particularly by a deep learning, the deep learning technique, which is a particular machine learning technique. And we have seen breakthroughs ranging from game playing to speech recognition, recommender systems, self-driving cars, and many other applications where deep learning was a crucial component to solve very difficult problems that have challenged researchers for many years before. And more recently, we have seen a big impact of deep learning also in the scientific computing community and computational mathematics. That's where I originally come from as a researcher. So people are using for example, deep learning to solve high-dimensional partial differential equations, or to discover governing laws of dynamical systems from time series data of the trajectory, and many other exciting applications in this kind of field of scientific computing. However, as always in life, there's always the other side of the coin, and there is a lot of skepticism too, and a lot of concerns surrounding deep learning techniques. We are all aware of issues regarding adversarial attacks in deep learning. So this leads to potential troubles with instability of deep learning approximations, either for classification or for signal reconstruction, for example. And this could be very troublesome in applications, for example, in the health sector, where instability could mean either wrong diagnosis or the potential to devise medical frauds. And so there are papers talking about the limitations of deep learning too. And I would like to in particular recommend this paper in the bottom right corner by Vegard Antun, Matthew Colebrook, and Anders Hansen from universities of Oslo and Cambridge University. where they talk about the limitations of neural nets and artificial intelligence, particularly from a mathematical viewpoint. I believe a subset of these authors, maybe all of them, I'm not sure, already presented their work at this seminar series. And in particular, they mentioned this Smale's 18th problem. So this kind of this controversial impact of the learning. On the one hand, we see breakthroughs. On the other hand, we see deep concerns. Kind of calls for a better understanding of the mathematical foundations of this field, and that's what Smale's 18th problem is about. So I'd like to go back with you to the paper where Smale listed 18 problems, mathematical problems for the next century. So they are really tough problems ranging from pure to applied mathematics. And the 18th problem, the last one, is called limits of intelligence. And it is characterized by the following question: what are the limits of intelligence, both artificial and human? So of course, this is a really broad and difficult question to tackle, but I really like the following passage from the statement of that problem by Stephen Smale. Smale goes as follows: a broader study is called for, one which involves deeper models of the brain and of the computer in a search of what artificial and human intelligence have in common and how they differ. I will look in a direction where learning, problem solving, and game theory play a substantial role, together with the mathematics of real number, approximations, probability, and geometry. So what I really like of this paragraph is that Smale is calling for a highly interdisciplinary approach to solve this very difficult problem. And that's what we're witnessing, even thanks to this very seminar series. The mathematics of deep learning has to rely on very high interdisciplinary approach, where researchers from different angles are tackling this problem of understanding the mathematical foundations of machine learning, and in particular deep learning, looking at the problem from different angles, from analysis, from approximation theory, from high-dimensional probability theory, and so on. So, inspired by these words, I would like to kind of set the focus for the talk. We will be focused on understanding the potential and limitations of deep learning through a rigorous mathematical and particular analytic approach. And I will do that by presenting two case studies. The first one will be so-called rating impossibility theorems in the context of identity effect, the so-called identity effect classification problem that is motivated by cognitive science. The second case study will be that of practical existence theorems. And here the problem of interest will be high-dimensional function approximation, mostly motivated by applications in scientific computing and uncertainty quantification. So these two case studies will first of all show, of course, they're related to my particular research path in this area, to my contributions, and they will hopefully kind of highlight how we can tackle this problem of understanding the mathematical foundation of deep learning from different angles. In the first case, we will use more or less elementary tools, mainly from I would say numerical linear algebra, a bit of probability theory, to have theorems regarding limitations of deep learning. So we will state so-called rating impossibility of certain classifiers. In the second case, we will investigate the potential of deep learning, and we will use actually non-elementary tools for more advanced research areas such as high-dimensional approximation theory or compressed sensing. Okay, so before starting with the two case studies, maybe this is an overkill for this seminar, but at least to set the notation, I would like to go very quickly through a definition of a deep neural network and deep learning. So a deep neural network, a feed-forward architecture, as we all know, is a is made by subsequent compositions of affine transformations and nonlinear component-wise activations. There might be ReLU or, for example, hyperbolic tangents or other choices. The affine transformations or the affine maps, they're defined by weights and biases that are trainable parameters. And we know that this type of approximator, function approximator, admits a very insightful graphical interpretation as a network. So, of course, we will be talking about architecture. so the size of the input, hidden, output layers, and the choice of the activation, and the depth, which gives a name to deep learning, the number of hidden layers. And of course, we have trainable parameters. So typically, you will need to solve some kind of optimization problem, which is called the training stage. So we're going to train the neural network by minimizing a potentially regularized loss function. So in the talk, we'll be in the setting of supervised learning. So we're given a data set, xi, yi, of training examples. And we will fit the trainable parameters to the data, possibly with regularization, where the data fidelity term will typically be of this form, sum of over the data set of scalar valued, some scalar value loss, which could be, for example, the squared absolute difference that gives you the least squares type data fidelity term, or it might be the cross entropy for classification problems. The regularization term will be typically a p norm. So, for example, for p equals 1, this will promote sparse set of trainable coefficients. So we have as many zero entries as possible in the weights and biases. And then you need to train this via typically stochastic optimization to handle the large size of data sets and use algorithms like SGD and Adam. Okay, so that's really basic stuff for this crowd. And but now I wanted to at least mention these things to make sure that everyone is on board also with the notation. So let's delve into the first case study, rating impossibility theorems. So I would like to start with a little question for you. So get ready to type something on the chat. So suppose that I tell you that the following words, for 2-letter words, are good. They are AA, GG, LL, and MM. And suppose I tell you that the following words are bad, AG, LM, GL, and MA. And now I ask you, are the following words good or bad? YY and YZ. So do you think that YY is good or bad? Please type in the chat if you what do you think about YY, the word YY. Is that good or bad? Okay, I read a bunch of goods. Yes, so that's a very, yeah. Now maybe everything is bad, but yeah, this is a trivial problem for a human being. This is really easy to understand. This is a good word. Is YZ good or bad? What do you think? YZ, letter YZ, type in the chat, please. Bad, bad. Yes, exactly. So that's very simple because we are just need to spot this pattern that the letter is good if it's composed by an identical, two identical words. Sorry, the word is good if composed by 2 identical letters. It's bad if it's not. So solving this kind of problem is trivial for human beings. And notice that you, in a way, okay, this is a very toy problem, but you were able to generalize outside the training set because in the training examples I showed you, I never mentioned the words Y, the letters Y nor the letter Z. Nonetheless, you were able to just spot the pattern and generalize it. Now I could show you 2 other symbols that might even be not part of any alphabet, and you will still be able to recognize if they're good or bad. So this first case study was motivated by this kind of problem. Can a machine learning, so this is a very easy task for human beings where they can generalize outside the training set. Can machine learning algorithms, and in particular deep neural network, do the same? So this was initially motivated by researchers in cognitive science and in particular linguistics. So spotting this kind of patterns and not only the identity, but potentially other type of structures, like, for example, AAB or ABB, this kind of symmetric patterns. Well, in the problem of syntax, then they help you understand if a given sentence is grammatically correct, or in the field of phonology, certain schemes, certain strings of phonemes might be good, so allowed in a certain language or not. So people were studying this kind of problems in linguistics. And Gary Marcus in '99 showed empirically with experiments in lab that even 7-month-old infants can generalize this type of easy so-called algebraic rules. However, simple neural networks were not able to generalize outside the training set this kind of structure. So this generated a heated debate in the cognitive science community, where people, the connectionist viewpoint was that, yeah, we can indeed learn this kind of thing just using a neural network and does not, without embedding the algebraic rule inside the network explicitly. Another viewpoint was that, oh, yeah, we need some kind of algebra-like structure in the network or in the brain, however it functions. So there was a heated debate here. There are two papers presenting two opposite viewpoints. And this somehow continued till very recently. There is this nice YouTube video. It's a debate between Joshua Bengio and Gary Marcus. They don't only talk about this, but this is part of that debate where they touch about more generally the best way forward for AI. I invite you to check out this video. It's really interesting. Okay, so motivated by this problem, let's set the notation for the identity effect scenario. So I will call the set of admissible inputs in the toy problem the two-letter words calligraphic X. I will call the rating assigned to a word lowercase r. So in the example I showed you, calligraphic X will be the set of all possible two-letter words using the English alphabet, and little r will be a rating between 0 and 1. So the probability of a given word to be good or bad. And then, of course, we have a training data set. In the example I showed you, well, these words are good, so we are assigning them a 1. These words are bad, so we assign them a 0. And then I will be talking in this first part of the talk about learner. So now the learner, this is slightly different from the usual statistical learning notation. So I want to emphasize this. The learner will be denoted as calligraphic L, not to be confused with regular capital L, which is thus the loss in the data fidelity part of the loss function. So calligraphic L is the learner. It takes as input the training data set, calligraphic D, and a new input, or potentially an input, could be or could not be in the data set, X. And then given these two objects, we'll assign a rating. And this can be anything. Could be the output of a feed-forward neural network or other type of architectures, maybe recurrent neural net, trained with SGD or Adam on a certain training set. So using this notation, we can have this first result, very general, and whose proof is outrageously simple, as you will see. So, okay, this is a first working collaboration with Matthew Liu and Paul Tupper, published in Neural Computation in 2022. So let's consider data set D and a transformation tau of the index space, such that the training data set is invariant to this transformation. So I'm not saying that the transformation is the identity, but like it just leaves the training set unchanged. Moreover, let's assume that also the learner is invariant to this transformation. That means that if you transform simultaneously both the training set and the new input that you give to the learner, that the learner will not notice this. Okay, so if you transform both, the learner is invariant to this transformation. Then we have so-called rating impossibility. So the learner will assign the same rating to the input X and to the transformed input tau X, which might be different, but the rating will always be the same. So in this case, it's impossible to distinguish X from tau X. So as I was told you, the proof is a one-liner. It's a ridiculously simple proof. We're really happy about that. It's a shorter proof we have in any paper. And it's simply based on these two properties. Okay, we first apply the learner to the data set and the transformed input. Then we use invariance of the data set to replace D with tau D. Then we use invariance of the learner to replace tau D and tau X with D and X. Okay, so this that's the main very general theorem. You might argue, well, potentially this sounds like a useless result. How do we apply this? So the rest of this first part of the talk will be trying to convince you that this actually leads to applicable results that lead to impossibility theorems for actual network architectures and training algorithms that are used in practice. And in particular, I will focus on the invariance of the learner question. So what kind of learners can be invariant, and with respect to what kind of transformation? So I will present these results. We have more extensions in the paper, but let's assume that now you have a data set of the form xi associated with some ratings, ri. And then we have the rating is produced by a model of this form. Now, this might or might not be a neural network. So what this model does is the following. If you give me an input, it first transforms it in a linear way through a weight matrix W, and then we'll do other stuff depending on other trainable parameters B. It could be, a deeper network. It could be something else. It could be linear, nonlinear operations. The important thing for this theorem is just that the input first passes through a linear operation, and then the model could do other things. Well, if you are in this scenario, and if we consider a transformation tau on the index in input space that is linear, and in particular, as a linear transformation is represented by an orthogonal matrix T, then we can show the invariance of learners of this form trained via SGD in the following setting. So let's assume that we randomly initialize the weights V0 and W0, and we minimize the following regularized loss. So in the data fidelity term, we don't have any constraint as soon as we have differentiability. And by the way, this result can be extended also to non-differentiable type of losses if you use subgradient descent type of algorithms. But for simplicity, let's assume to be in the differentiable case, we have any generic data fidelity term. On the regularization term, we do have some constraints. So if you only use the Frobenius norm on the first matrix W that takes the input as the very first thing, and if you use any possible regularization term here for the other weights V, then you have the impossibility if the initialization on V0 and W0, first of all, they're independent, and they are, so if you transform W0 by this transformation T associated with tau, then you have that you're not changing the distribution of the initialization of W0. So they're equidistributed, W0T and W0. Notice that typically when we run SGD, let's say with random initialization like normal center Gaussian variables, then this will happen because the normal distribution is invariant when you multiply that by an orthogonal matrix tau. Okay, it's invariant, is rotation invariant. And then, okay, under these conditions, we have that the learner that now employs the given architecture with the trained parameters after k iterations of SGD will be invariant with respect to this transformation tau in distribution. Okay, so now there is randomness involved in this statement, but you can have a deterministic version of it. So in the random case, we talk about impossibility of rating in distribution. And this can be extended to other training algorithms, such as the Adam algorithm or other models, for example, of this form, where you might have, for example, you might input the two different letters of the word in this way. By passing through the same, you might have a sequential type of model, like a recurrent neural net, for example, an LSTM. And it's possible to generalize the theorem also to this kind of models. Okay, so this theorem tells us about under which conditions we can hope to have the invariance of the learner. So let's go back to our motivating example where I asked you the little quiz if the words were good or bad. So I will show you a particular transformation that is useful for our purposes here. So we have two-letter words, and let's define tau in the following way. If the second letter of the word is a Y, then we trade it for a Z. Okay, so we exchange it with a Z. On the other hand, if the second word is a Z, we exchange it with a Y. So remember that Y and Z were not shown in the training set, but we wanted to generalize the kind of identity effect classification to words that contain Y or Z. If your second letter is not a Y nor a Z, then we just leave the two-letter word unchanged. Okay, so now in the situation where I'm not showing you Y nor Z in the training set, of course, this transformation is leaving the data set unchanged. So D is invariant with respect to this transformation because we'll always be in the third case. because the second letter in particular will never be Y nor Z, which are not in the training set. However, now the properties of tau will depend on how we encode the letters. Notice that up to this point, I've told you nothing about the encoding of the inputs. And this will be a key step. So let's say we encode the letters of the English alphabet in R26, for example, with 26 vectors, V1, V26. Then this type of transformation is linear. We can be represented as a linear transformation. However, it will have different structure or properties, depending on what kind of encoding we are using. Now, let's start easy. Let's assume that we use the classical one-hot encoding, so the canonical basis to encode each letter. Then you can check that the matrix associated with this transformation is just a permutation matrix. In particular, we are in the framework of the previous theorem because it's orthogonal. If, on the other hand, V1, V26 is only an orthogonal basis, not necessarily a one-hot encoding, then the matrix will still be an orthogonal matrix for representing tau. However, if you're only using linearly independent vectors V1, V26, then we can only conclude that the matrix associated with tau is invertible. So we will not be able to conclude impossibility of rating for the learner. And let's check why this implies impossibility of learning in this particular case. So our theorem tells us that the learner, based on the given training data set, and will assign the same rating to tau of x and x. Now, let's pick a particular x. Like in the initial example, let's say that the word little x is given by the two letters capital Y and capital Z. Then the transformation according to this tau will be the word YY. And in particular, this conclusion can be interpreted as the learner gives the same rating in distribution to the letter YY and YZ. So we'll probably never be able to distinguish a good word from a bad word, no matter how many iterations of SGD you use, or even add them in our extension, but no matter what kind of architecture you're choosing, like how many layers you have. So that's why we call this type of result impossibility theorem, because the learner will be probably unable to generalize outside the training set in this type of scenario. So I'd like to conclude this first part of the talk by showing you some numerics that consolidate this theoretical finding. So first of all, we'll apply in the motivating example with two-letter words, we're applying an actual deep learning model. So I'm showing you results for different learners and encodings. So in terms of learners, we're going to use feed-forward neural networks of moderate depth. You can go higher, but we have noticed that this didn't really have any impact on the results. So here, if you move from left to right, you're going to have depth 1, 2, 3 of the learner, trained with SGD in this particular example, but also results are identical for Adam. And if we move along the row, we have on the top row, we're encoding letters as with the one-hot encoding, so basis of the canonical vector, vectors of the canonical basis. In the second word, in the second letter, we are using orthogonal encoding. In particular, we're generating a random orthogonal encoding by generating a random orthogonal matrix from the Haar distribution. In the third row, we are using a non-orthogonal encoding, a so-called distributed encoding. So we encode each letter by activating 3 random bits out of the 26 available. Okay, so the representation of each letter will be all zeros apart from 3 ones that will be placed in 3 random positions. So with high probability, in this case, you have a linearly independent set, but in general will not be orthogonal. So what are we looking at here? The first 2 columns, this will be the rating assigned to by the learner to different letters. So the first 2 columns are always letters within the training set. So the first letter is the letter A, so the word AA, which is inside the training set. And so we want to see a rating as close to 1 as possible. So this is measuring the training error. Little x, little y is here. Since there is a randomization involved in the generation of the training data set in this example, this will be the first bad word in the training data set. So here we want to see something that is as close as possible to 0. Of course, this is just the training error. We would like to test the learner on some unseen examples. And the other words here involved Y or Z. So letters that were not shown in the training set to the learner. And we can see that if we encode letters with a one-hot encoding or with an orthogonal encoding, essentially the ratings given outside the training set are always around 50%. So there's no ability of the learner to generalize outside the training set. The deep learning is not able to break this kind of orthogonality barrier during the learning. However, if we encode letters in a non-orthogonal way, then we can see some generalization. So it's not perfect. Probably this can be optimized if you're more careful with training and choice of architecture. But you do see a partial generalization now. The good words are recognized, are given higher rating than bad words in the test set. So that's what we wanted to observe. An impact at the conditions, the learning and training conditions, are all the same here for all the methods, but we're only changing the encoding. So we wanted to show the effect of the encoding on the ability to generalize. And in the one-hot encoding, if you think about it, is not very surprising, because by representing letters with vectors of the canonical basis, if you never observe Y or Z, essentially you're never activating certain input neurons. So it's natural that you never train the corresponding weights. That's very natural. But the orthogonal encoding is less intuitive, because now potentially we're activating all the neurons in the input layer. However, they are chosen in an orthogonal way, and somehow SGD and the nonlinear activations, they're not able to pass beyond this orthogonality barrier. So I find the results in the second row more surprising. So we wanted to also test this to a different model now involving the MNIST data sets. So now we want to recognize if pairs of digits are identical or not, or in other words, if a two-digit number is palindromic or not. However, now the input are images. So I'm giving you two MNIST images, and I would like to understand if they represent a palindromic number or not. And now we're considering the following model. First, we perform computer vision. So first, we run a typical classifier just to classify individual digits. And we here use just the one from the Keras tutorial that gives you good performance. So first, we classify each singular digit. And then this will produce a vector of probabilities. So now this will be, for example, an 8 with fairly high probability. In some cases, you might be not clear here, for example, if this is a 3 or a 5. And we can think about this as an encoding. Okay, first of all, here, this graph, you have to read it from right to left. Matthew liked to think about this in this way. So the inputs are on the right, and then we are feeding the network from left to right. So first we run through a computer vision model. There's the first network. We run the second digit through the same model, and we obtain these two probability vectors. And we can think about these as encodings. So in a way, we are encoding digits into a 10-dimensional to 10-dimensional vectors. And we can think about it as noisy one-hot encodings, because if you're very confident about a digit, then the probability of the corresponding in the corresponding entry will be very close to 1, and you will have very close to 0 numbers in all the other entries. And so in some cases you might be undecided. So in that case, it's a large perturbation of a one-hot encoding. And in the setting, we then feed these two encoded digits into an identity effect model to see if we can spot if they are the same digit or not. So again, we're not showing certain images to the data set. So we just train the identity effect model. The computer vision model is able to recognize any digit. However, the identity effect model will only see training examples of digits from 0 to 7, and we would like to generalize to 8 and 9. We choose to train the computer vision model in two ways. First, we consider a highly, so this is a loss, training and test loss as a function of the epoch. First, we consider a severely undertrained computer vision model, and then an optimally trained computer vision model where the test loss is minimized. We'll consider these two scenarios, and we will see that they will have a substantial impact on the ability of the second model, the identity effect model, to generalize. In fact, we have a similar, I'll show you a similar set of results as before. So here we are varying the depth of the identity effect feed-forward network from left to right, from 1 to 3. And we're changing the encoding, but now the encoding is given by how much you train the computer vision model. So the first row will be an undertrained computer vision model. The second row will be an overtrained computer vision model. So again, according to our theory, we call that having an orthogonal encoding is bad because that will lead to learning impossibility. So the closer you are to an orthogonal encoding, the worse the identity effect model will do in terms of generalizing outside the training set. In this case, undertrained means you are far from the one-hot encoding because there's a lot of noise. You haven't trained the computer vision model perfectly. Overtrained means you're getting closer to the one-hot encoding. And in fact, we can see that this has a crucial impact on the results. In this case, the first two columns are ratings assigned to images of digits in the training set. In the second two columns, in this case, we have digits that were in the training sets, but images that were not in the training set, because in this case, we have, different images might represent the same image. So here, this is a partial generalization just to the image level, not to the digit level. And in the last 6 columns, we have numbers with 8s and 9s. So examples that were not shown to the identity effect model during training. So again, when we use an undertrained computer vision model, so we are far from the one-hot encoding, the ability to generalize, to spot good from bad numbers, in this case, palindromic versus non-palindromic numbers, is better when the model is undertrained as opposed to overtrained. There's also an impact of depth here. We haven't investigated this too closely, but what we wanted to see was the impact from moving the row from undertrained to overtrained. And we see consistently that the rating, the generalization is better for undertrained computer vision models. In a way, there's even a almost philosophical reflection here to make. So the computer vision model is focusing on the single numbers, on the single digits. So in a way, it's focusing on the details. The identity effect model is trying to classify the bigger pattern. So in a way here, this is telling us that if the model is focusing too much on the details, then it kind of loses the big picture. On the other hand, if the model is not very accurate on each detail, then somehow is able to better grasp this noise that comes from undertraining the computer vision model. Actually helps in generalizing the bigger pattern and seeing the big picture. Okay, so that's the first part of the talk. Maybe that's a good time to stop and ask for questions, because then I will shift gears and there will be another topic that is quite different. So if you have any question about this first part of the talk, please feel free to tell me. You can also save it for later if you want, I guess. But let me know now if there's any question about the identity effect case study.
Yeah, feel free to unmute or ask the questions directly.
Yeah. Let's see. There is something in the chat. You don't seem to use any particular properties. It seems to me that your results are valid for any optimization scheme. In other words, that depend only on the geometry of the lost landscape. And I'm missing something. No, yeah, I think that's really great remark. So essentially, what this kind of result relies on, you see, like the stronger assumptions are this one. So how you initialize the weights. So this will have an impact. Particular, we haven't noticed this in practice. We tried different initializations, and we were still observing rating impossibilities. But at least at the theory level, having this invariance in distribution of the initialized W with respect to the transformation is a crucial assumption. The other crucial thing is this regularized term. If you have something else, if you regularize W with something else, maybe, for example, with an L1 norm or an LP norm with P different from 2, because now we have the Frobenius norm, well, then the theorem doesn't hold anymore. The Frobenius norm is a crucial thing because really, yeah, here the main argument is geometrical, because the basic idea is very simple. Essentially, if you transform the input X by the transformation tau, then you can substitute X with TX. And you can always think about WTX either as W parenthesis TX or WT times x. Okay, so you can move the transformation to from the input to the first weight. That's the whole trick here, mathematically. And if you use the Frobenius norm, changing the weight by a right multiplication to an orthogonal matrix doesn't matter because it leaves the Frobenius norm unchanged. So yeah, purely here there's geometric intuition. However, you have to be careful, not any optimization method works, because then we actually go through the iteration of SGD and show that this invariance is preserved through the iterations under orthogonality. If you use Adam, then you have to be careful because there are some nonlinear steps there. And actually, general orthogonality doesn't work anymore. At least in our theory, we're not able to prove invariance for Adam-trained models for general orthogonal matrices. But in that case, we need permutation matrices, which is still covers the case of orthogonal encoding, but not the case, for example, sorry, of one-hot encoding, but not the case of orthogonal encoding. Even though the numerics seems to suggest that even if you use Adam, still orthogonality is enough to make learning impossible in this case. Okay, hopefully this clarify. Yeah, the nonlinear step can make a difference on how the invariance is propagated through the iteration step. So yeah, that does make a difference. Well, thank you. This was a really important point. So okay, so now it's I think I'll move to the second part of the talk, and of course, I'm happy to take more questions in the first part, even at the end. So here I'll switch gears a little bit. So now the tools that I will use for this type of theorems, called practical existence theorems, are different. They involve more high-level tools such as high-dimensional polynomial approximation theory and compressed sensing theory. So the motivation here is really approximating a multivariate function of an input x as fx. The input is d-dimensional, as d can be very large, potentially even infinite dimensional. We would like to approximate this object given pointwise samples. Okay, so there's a typical function approximation setting, or if you want, regression setting. The motivation I had in mind here is the approximation of parametric models. So typically f of x could describe a physical process that might be modeled by, for example, a differential equation. And the inputs here are the parameters of this differential equation. Then you run the model through a black box. For example, you simulate the numerical solution of a PDE for given parameters, and then you have an output that might be the solution of the PDE, or maybe a quantity of interest of the solution. And you want to approximate this kind of parametric model. So this has been widely studied in the field of uncertainty quantification, where a key task is so-called surrogate modeling. We would like to approximate this high-dimensional object by a surrogate of it in order to perform uncertainty quantification efficiently. When you have inputs that might contain uncertainties, then, for example, to perform statistical simulations on the parametric model, it's very nice to have a surrogate model that is able to approximate the true model in a fast way so that you can sample more. And applications range from fields from weather and climate science to biology. And I do encourage you to check out this book, Uncertainty Quantification by Ralph Smith. If you're curious about that, there's a nice first chapter about many examples of parametric differential equation models that are considered typically in UQ. Okay, so first I will explain how to achieve approximations through sparse polynomials. So let's assume for simplicity that our function is defined over a high-dimensional hypercube, -1, 1 to the d. Then we first define a one-dimensional basis of orthogonal polynomials on the interval -1, 1. And then we tensorize these orthogonal polynomial bases in each dimension. For example, you might consider Legendre polynomials. This tensorization, so these are orthogonal polynomials on the interval -1, 1. This tensorization preserves orthogonality, actually orthonormality, and you have an orthonormal basis of L2, where this basis will be identified by multi-indices in the space of indices n0 to the d. Okay, you can always think, so these are Legendre polynomials. You can think about them as kind of not too far from Fourier basis functions. They oscillate at higher and higher frequency on the interval. And it's nice to keep in mind the multi-index space. So in this figure, I'm showing you the tensorized polynomials, for example, in 2 dimensions. But I will use this notation in some slides. This is the multi-index set. Okay, so for example, the multi-index 0, 0 means tensorizing the zero order polynomials on both directions. So you get a flat constant in 2D, or you might tensorize a constant against a linear thing, and you get this kind of plane, and so on. You can tensorize constant with parabola, parabola against parabola, cubic against parabola, and higher degrees. So this kind of construction is very popular in approximation theory, and we would like to, in particular, construct a sparse polynomial approximation. So we like to construct an approximation of f hat, that is made by a linear combination of polynomials, but the linear combination only activates a small number of terms. So the L0 norm is as small as possible. What kind of class we focus on? Because here we need to approximate functions, but since we are in a high dimensional case, typically we suffer the curse of dimensionality, and in general, it's too challenging to approximate any possible function with a d-dimensional input. So we'll have some smoothness assumption that will allow us to make rigorous analysis. And the smoothness assumption we will assume is that f admits a holomorphic or analytic extension to a Bernstein polyellipse. So the Bernstein polyellipse in one dimension is a very classical object in numerical analysis that people have been using to prove decay rates for polynomial approximation theory. Here, the generalization to multiple dimensions is more recent, and this class has been studied since this seminal works by Cohen, DeVore, and Schwab in constructive approximation methods. And under this assumption, you can prove a formal decay rate for the best S-term approximation error. So the best approximation you can achieve of your function that only activates S polynomial coefficients decays exponentially with respect to this term S to the 1 over D. So there is an impact of the dimension, but the decay in S is very, very fast, exponential type. So this is not just an abstract assumption, and I'm just showing you the exponential type rates. You can also show algebraic decay rates that are actually independent of the dimension, but they're algebraic, not exponential. For simplicity, I'm only showing you the exponential rates. And this is not just an abstract assumption. You can verify that the holomorphic extension assumption holds for several parametric differential equation models, such as the diffusion equation under suitable assumptions on the parameters, such as the parametric diffusion, the parametric harmonic oscillator, the heat equation, and so on. You can even parameterize the domain of the PDE. So you can parameterize the shape of the domain, and you can show that there's the holomorphic assumption there too. This has been studied in approximation theory quite extensively in the past dozen of years. And now we want to build an approximation. So there's an issue about anisotropy. So how fast does f vary with respect to each variable? So somehow it's key to understand the importance of each variable to construct a good approximation, to understand which polynomials we should activate. Okay, maybe we should have more polynomials in a higher degree with respect to a certain variable, and lower degree with respect to other less important variables. And the more formal way to measure this kind of anisotropy is the size of the Bernstein polyellipse rho. That's the size parameter. So if you know the anisotropy in advance, you might fix the polynomial space in advance. And then there's many classical techniques to construct optimal polynomial approximations in these fields. For example, you might do interpolation via sparse grids. You can use quadrature methods where you approximate the coefficients. That is to say, you approximate the integrals via some kind of form of quadrature rule. You could use least squares, possibly weighted least squares polynomials. But all these techniques require you to choose to know the optimal approximation space in advance and to focus on that and then run your approximation method. And these are all sample efficient if you know the space in advance. However, if you don't know the optimal polynomial space in advance, we are in front of unknown anisotropy of your function. And so you might either use greedy adaptive methods where you explore the polynomial space in an adaptive fashion by building it step by step in an increasing fashion. And this can be very efficient computationally. However, There's no, as of now, comprehensive theory for them. In this talk, I will focus on compressed sensing and deep learning techniques for this task, when you're trying to approximate a high dimensional function without knowing the anisotropy in advance. And so, in particular, compressed sensing, so there's this first step. If you're able to identify a large enough ambient set lambda that might not be the optimal space since the very beginning, but somehow contains the optimal polynomial space, then you can set up optimal compressed sensing methods. Because first, you truncate the expansion in this this possibly larger, much larger than the optimal set polynomial space. Then we collect Monte Carlo samples using a number of samples that is much less than the dimension of the ambient set. And we build the usual discretization by essentially evaluating the polynomials at the sampling points and the function at the sampling points to build the observation vector. We have a discretization of our approximation problem. And you might solve, you have any options here, but one good possibility is to solve the square root lasso problem, a weighted square root lasso problem, where we minimize a data fidelity term given by the L2 norm of the residual plus a weighted sparsity promoter regularizer, which is the weighted L1 norm. So this has been, again, studied for the last decade in several forms, proposed in literature. Now I'm proposing square root lasso, which is a recent innovation because it gives you optimal ways to tune the parameter lambda that are independent on the noise corrupting the measurements. Because keep in mind that this scheme gives you a linear system like that, but it will be corrupted by noise that it will always be unknown a priori because it will depend at the very least on the truncation error on the samples, but potentially by other sources of noise. There could be numerical noise or physical noise if there are real experiments or sampling devices involved. Well, for this kind of scheme, we can prove rigorous convergence guarantees for compressed sensing and for a specific choice of the ambient set. So if the ambient set is chosen as a hyperbolic cross, so let's say we want to use m samples, then if you define this parameter m tilde, which is just m divided by some log factors and a universal constant, then we can fix a hyperbolic cross polynomial space of prescribed dimension. And hyperbolic cross is just a polynomial set of this type. Okay, this is a hyperbolic cross in 2D. If you do that, then you can prove exponential decay rates for the compressed sensing approximation to f that decay exponentially according to this parameter m tilde. So essentially, we're able to achieve now the same type of decay rates as the optimal best external approximation rates, but now we're actually computing the approximation via compressed sensing from a finite amount of samples, m. Okay, so this result can be found, more details about the result can be found in my book, co-authored with Ben Adcock and Clayton Webster, just published in 2022. One of the key ingredients is that the hyperbolic cross contains all S sparse lower sets. So a hyperbolic cross of order S contains any so-called lower set of cardinality S. And the lower set is a red index set like this one that doesn't have any gap or hole in it. So somehow this enables you to capture the best approximation available when you activate S coefficients, because the smoothness assumption, that is F is holomorphic, essentially allows you to restrict your attention to lower sets. That's a very high level idea of the proof, but if you're interested in more details, I encourage you to check out our book and its companion website, sparse-hd-book.ca. Okay, so deep learning, how does deep learning comes in the picture here? We have seen a great amount of progress in the field of deep learning approximation theory, and I do recommend this nice review paper on deep learning approximation theory that I'm sure many people in the audience are familiar with. I will not cite all the results in this area. There are very many. I apologize if some people in the audience have published in this and they don't say their name here, but there's so many interesting results here that it's hard to cite everyone here. So you might focus on different function spaces like sublet spaces, piecewise smooth functions, band limited function, Baron function, and so on. And typically you have this type of existent result. So you're able to establish the existence of a neural network that is able to approximate functions in that class up to a prescribed accuracy. And typically, theorems in this field are constructive. You're able to construct what kind of network is able to achieve that accuracy. And the results for our class of interest, that is the holomorphic functions, there are also this kind of existence approximation theoretical results that were recently published. However, these kind of results beg two key questions at least. So beyond existence, and this is in the this kind of results come from the line of work of universal approximation theoretical results, right? So, however, they leave this kind of questions unanswered. That is, how many data points do we need to achieve the prescribed accuracy, and how do we train the network to prescribe a given accuracy over a class? Also, how does deep learning-based approximation compare with polynomial approximation via comprehensive? So these results these questions are answered by this kind of so-called practical existence theorems for deep neural networks. So a first theorem of this type was published by Ben Adcock and Dick Dexter in a form that is different from the one I'm presenting here. Then we refined it in a subsequent paper with Ben, Nick, and Sebastian Moraga in 2021. We're also extending it to the case of Hilbert-valued functions, which I'm not presenting in detail here for the sake of time. We're also working on a Banach-valued case for function approximation. So the type of result you're in front of is similar to the comprehensive conversion rate result. Now, you're given a set of uniform sample data, and m data points. Then you define this m tilde, that is m up to log factors. And we are able to say that there exists a class of deep neural networks for which we can provide explicit bounds for depth, number of training parameters, and number of non-zero parameters. There exists a regularization functional that is a certain norm of the trainable parameters of the network. And there exists a regularized loss function that will be able to give you the network you're looking for. And this network will achieve the same exponential conversion rates as compressed sensing, and in particular, as the best S-term approximation over the class of holomorphic functions with high probability, because of course, these are all statements that depend on the randomly sampled data. And here you see this objective, the loss function bears resemblance with the square root loss function that we needed to use to have a tuning strategy for lambda that is independent on the noise level, in particular on the truncation level. So that's a crucial ingredient of the proof. We can also validate this numerically, and in the interest of time, I think I'll skip this because already it's already 1 p.m. If you're interested, I can go quickly during the QA time. And I also want to mention that it's possible to prove this kind of convergence rates for compressed sensing, not only in the function approximation case, but also when you're trying to approximate PDEs defined over high dimensional domains. So now it's not the parameter that is high dimensional, but the domain that is high dimensional. Similar ideas can be used to devise compressive spectral Fourier collocation techniques with recovery guarantees, where you can probably show that the curse of dimensionality can be less than in the number of collocation points. So this relies on not anymore on orthogonal basis, but on randomly sampled bounded risk basis. And we're currently working on providing practical existence theorems for the case of numerical approximation of high dimensional PDEs. Okay, so to sum up, we, inspired by the initial words by Stephen Smale, we have illustrated ideas from a variety of fields that can help in providing insights into mathematical foundations of deep learning. In particular, we have seen results that identify limitation or potential of deep learning with the impossibility rating theorems or the practical existence theorems in two different contexts: identity effects motivated by cognitive science, and high dimensional functional approximation motivated by scientific computing and uncertainty quantification. Of course, there's much more work to be done. And with this, I would like to conclude and thank you very much for your attention. These are references, the main references for the work I've been presenting, my book, and the two main papers for impossibility theorems and practical existence theorems. And thank you very much, everyone.
Yeah, thank you, Simone. Thank you very much. Any questions or comments?
Hopefully, I didn't kill the audience. Maybe I did. Sorry.
Yeah, I think it was nice. I think it's a nice survey. Yeah.
Okay.
Did you want to cover like an extra slide or two, or are you done?
No, it's fine. I mean, there were some numerical results here where essentially we show that we compare compressed sensing with deep learning. So in a 30-dimensional parametric diffusion equation, the physical domain is 2D, but the parameters are 30. And essentially, we compare compressed sensing type approximation. Here we are actually approximating the Hilbert valued map, that is the solution map, mapping parameters to the PDE solution. And the solid line is compressed sensing, and all the dashed lines are deep learning for different choices of architectures, so width and depth, and also for different choices of activation. So the take-home message is that actually this practical existence theorem tells you that deep learning can do at least as well as compressed sensing, but actually the numerics over the class of holomorphic functions. But the numerics show that if you're careful with parameter tuning, actually you could do a bit better. So for example, this tan H activation is able to outperform compressed sensing even in this very smooth function approximation problem where the parametric PDE gives you a holomorphic function. So yeah, maybe I'll just say this, that you can validate the kind of conclusion also numerically here.
Okay, thank you.
All right.
All right. So any questions, comments? Okay. Yeah, there is nothing. Okay. Thank you.
All right, folks. Yeah, feel free to write me if you want for any question. And thank you again for the invitation, Boumediene. And I'll see you around in Montreal, I guess, these days.
Yeah, exactly. Yeah. Thank you. Thank you again.
Okay.
Thank you, everyone. Bye. Bye, everyone.
Bye, everyone. Bye.